Okay, so George, take it away.
Okay, well, thank you for being here. So this is a bit of a last minute task. So I thought I'd do a talk that's mostly demo, because I sort of think that doing a just badgering you with all the math that's in the library will be kind of boring. And kind of the whole point of, and the major effort that went into this library was actually make the math work together. So my grand plan is to actually go do a deep dive on two proofs to show you how, in each case, bits of the library work. So I've picked one proof that's very elementary in terms of math, but that I have particular fondness for. And that's a proof about the combinatorial Jordan property for planar hypermaps. And I'm especially proud of this proof because Tom figured out that it was also useful for proving FlySpec. And so there's a formalization of it in FlySpec. And the proof you're going to see is significantly shorter than the one in Hall Light for FlySpec. And I think it has something to do with how the library works. The advantage of this is that there's very little math in terms of how much you need to know from high school. There's probably more that I need to explain to you. That's kind of the danger, I guess, of doing this by example, that you may get more involved in how the proofs work than how the proving works. And so I'll deliberately cut short if I'm running out of time so that I can address the second proof, which is more mathematical in nature and is actually fairly good at showing off the various parts of the library. So I think every of the sort of fundamental algebraic things that we've built into the library actually show up in this proof. And so that's the proof of Wedderburn's little theorem, adapted from Witt. And so that's the proof that if you have a finite domain, then it's actually a finite field. For a finite domain, multiplication is regular, so you necessarily get inverses, so it's always a division ring. But the tricky part is showing that it's commutative. And that's actually a proof that was done by Christina Szorekova when she did an internship with me in Microsoft over next to the station. So that's pretty much her proof, just a little refactoring from me. So that's the slide I showed. Just a brief. I'll be very brief in the overview of what's actually in the library. So the most fundamental part, and the part that was sort of hardest to get right, was the combinatorics. Just getting the nitty-gritty pencil and paper stuff to work properly so that we can move on and do actually significant math without fighting with the pencil and paper. And then there's quite a bit of undergraduate algebra and fancier group theory stuff, which I won't get into today, and constructive math that sort of actually is used in the second proof. So I'll just mention it when we see it. Okay, where is this? So that's the big library. And this is just to remind you of the scale of things, where a single file would typically have a bunch of things. We'll see this for the second proof, because it actually involves, even though it talks about fields, it actually involves quite some bits of group theory. And the reason I'm looking at sort of bigger theorems is that it's really uninteresting to look at proofs of theorems in basic libraries, because they're all trivial, and there's not enough automation in Cog that you can say by auto at every line, but it sort of all fits in a line. So from my perspective, there's almost no effort in proving these, whether there's automation or not. So automation for doing this is sort of, I guess, overkill. And so we'll get a better feel of how much hand-holding Coq needs when you look at doing a proof in anger and trying to combine stuff. So a little bit about the general picture. So a lot of this picture is the, which again I showed 2 weeks ago, is sort of the familiar algebraic hierarchy. The thing I'd like to point is that the hierarchy is built on a combinatorial. So everything that's algebraic also has a bit of combinatorics built into it, in the form of being able to compare, giving means of comparing two values. Now this is sort of implicit if you work in classical logic, for classical first order logic, where equality is a built-in notion. And deciding equality holds because you just assume that everything is decidable and you don't care how things are decided. So in this case, having this at the bottom lets us basically do, and there's something similar about having choice for countable types. And having these two at the bottom mean that we can do algebra as if we were in classical logic. So it's standard math, just with a thin veneer of paint that makes it pass the muster of a constructive logical system without needing to add a brute force axiom. And I also wanted to point out these bits here about having not only the hierarchy but also the morphism hierarchy. And that comes up, and what comes up more directly is going to be the predicate hierarchy. And we'll see those in action in the second proof. And I guess I kept those slides to insist that what's important about these libraries is not that you've defined the interfaces, is that you actually have instances of these interfaces, and that you can talk about the real mathematical objects that interest you, whether they're matrices or subspaces or polynomials, and then call upon everything that's in the interfaces implicitly. That's the whole point of doing this. There's no point in doing lots of abstract constructions and then not being able to use them, or having to force the hand of the prover every time you want to use them. And that's most of the code that implements this hierarchy is actually code. It's not code that proves theorems about rings, because those are trivial. It's code that lets you have those interfaces work as seamlessly as possible. Okay, now on to the first example, and to talk about the proof, I need to explain what the proof is about. So the proof is about this combinatorial notion of the Jordan curve theorem, or equivalent of the Jordan curve theorem, for combinatorial hypermaps. So I have included a little reminder of what a hypermap, a combinatorial hypermap is. Well, it's been in Yves' talk and in Tom's talk. So here's my take on them. If you want to describe a map, and the traditional way of describing a map is saying, oh well, really you've got these regions and they're separated by lines, and the line meets at points. So line meeting at point, that's a graph. That should be good enough. And of course that doesn't really recover the organization. If you try to prove theorems, you're sort of constantly having to go back to the embedding of the graph inside some real variety. And that makes your arguments a bit of a mess. So the proper way of doing this is being just a little more precise and taking as your basic points not the actual intersections, but the corners of the regions. And then you can actually write down the navigation data. So little green arrows to go around faces, little red arrows to go around nodes. So you essentially have two permutations, and you can compose the two permutations, which if you start from a plane graph, gives you a permutation that only has 2 cycles. And those cycles correspond, so the red cycles that go around nodes correspond to nodes, the green cycles that go around faces correspond to faces, and then the blue cycles go across edges, and so they correspond naturally to edges. And the whole point of a hypermap is that you just drop the restriction that edge cycles have to have length 2, so you allow hyper edges. And then the theory becomes completely symmetrical. Or rather, to make it symmetrical, you put the constraint that you've got these, you've got to have all these green, red, blue triangles. So as long as you have these identity, this sort of three-way identity, well, of course that implies that you had permutations in the first place. And you have a presentation that's symmetrical in the 3 relations. Moreover, the planarity can be described by symmetrical arithmetic relation, just counting the number of red, green, blue cycles. So it's a very nice way of describing concretely what a planar map is and being able to reason with it.
I take it that this only works for finite graphs, though.
Yeah.
So is there a way to capture what a planar infinite grid, say, or something like this?
Well, you don't need to, because it's a consequence of logical compactness that you only need to show the 4-color theorem for finite maps, and then that automatically extends to infinite maps. So because any counterexample would have to be finite, essentially. And it actually is done in the formal proof. So that's how you describe a map. So this planarity criterion is nice because it's easy to establish. It's easy to show that when you change maps to establish that it's maintained, or under which condition it's maintained. It's not so easy. It's not so good for doing the one thing that you want to do if you want to exploit planarity, which is to chop up the map by picking a part that's inside a contour. And this is the one thing you need to do to prove the 4-color theorem. You need to identify special places in the map that are easy to color, and then and then see that anything that happens inside only interfaces with what happens in the outside around the border. So that's essentially the Jordan curve theorem, and the classical proofs actually invoke the Jordan curve theorem. It turns out that when you do the proof formally and go through this combinatorics, you don't need the analytic for Jordan curve theorem. You can use a substitute, which basically works by looking at exactly what happens when you divide it around the contour. And so if put down the darts, the little corners, and the red and green arrows. And if you reduce this to the exact border, you see that a contour is really a path that alternates between, say, forward green arrows and backwards red arrows.
This is always a polygon, right? Like you do not need Jordan curve theorem in its full power. You just need the polygonal version. Or
yes, you probably could do with a polygonal version, but then you'd essentially need the combinatoric one. And it's actually much easier to establish the planarity using the Euler formula. I won't get into that. So now that we know what a contour is, so I've got other slides explaining this, but I think I'm much better off actually drawing this out. So what does the Jordan theorem says? It says if you have a contour, you can't have a path that starts on the inside, somehow crosses over and lands on the outside. So that's the thing that should never happen. And if you translate this combinatorially, maybe I should move. If you look at the contour here, you can see that all the red cycles are on the inside and all the green cycles are on the outside. So the way you can tell that a path is starting from the inside is because you've got, okay, so should pick a different color for contours.
There's a green one over here.
No, I'll use, so you start red on the inside and you land green on the outside. And of course, because this point is not on the contour, this edge has to be the other color. And similarly.
What is this, the path exactly?
So the purple are contours, so they're paths that go green in one direction and red, take the red arrows in another direction.
So these are paths which follow the lines of the.
They follow the little red and the little red and green arrows.
But then what's the
But then-
interpretation in the original graph?
The implication is that this is how you separate. This is what you get when you look combinatorially at what a contour or Jordan curve would be.
It's basically connecting the dots on the,
Right. And so if you so describing this as trying to prove things with this kind of diagram is would be extremely messy because you've got three different bits of curve. So the trick to getting this to be simple is to say start at one point here, go around here, go around the green edge here, go all the way around, and then stop here. So now I've traced a single contour. And the only things I haven't traced are these two.
Those are directed, right?
Yeah.
Which way are the arrows going? In the little green.
So here I'm taking the green arrow forward. Right.
And the red arrows pointing back.
And so the red arrows pushing in the other direction. Okay, so if you redraw this, you see that what you have is one big contour, and then you've got, so it's taking the red arrows in the other direction, and then you've got two overlapping red arrows. And so what we want to prove is that if we have a map that satisfies the Euler condition, then it never has a diagram like this. If it doesn't have a diagram like this, then this can't occur. So we can define the outside as whatever is connected to the border through reds, and the outside is whatever is connected to greens. And the things that aren't connected, you can assign to either inside or outside. So now, how do you prove this? Well, basically by induction. Assume you have a planar map, and you have one of these forbidden forbidden contours. Then what we can try to do is get a smaller hypermap that still has the contour. And as we go smaller and smaller, ultimately we get to just 3 points. And once we have 3 points, we can compute the Euler genus and figure out that this can only be embedded in a torus. So how do you reduce the map? Well, it's actually you do the most simple operation, and so this was proposed by a gentleman, David Walkup. And so the idea is simply, okay, you want to have things smaller. Well, locally in a hypermap, everything around the dart looks exactly the same. It always looks exactly like a hexagon like this. And I guess to be complete, I should fill in the triangular identities. So, here and a. So let's suppose we just wipe out this point. Okay, so now we've got, if we want to create a hypermap, we've got dangling edges. So we've got to reconnect them. So the obvious way of doing this is to take two dangling things and reconnect them together. So let's do this for the greens here. And blues here, so this is called suppressing a point in the permutation. And the great thing about suppressing a point in a permutation is that basically you don't change the cycles. You might get one fewer cycle if that point was isolated, if this were degenerate, but otherwise you have the same number of cycles. So it's great for seeing the identity. Unfortunately, we can't do this for the reds because we need to keep these triangular identities. So now we've decided that we've got green here, blue here. The only way we can complete the identity is to destroy an additional arrow. And connect things this way. And it's very easy to see that if you start from a planar map, after you've done this operation, it still has to be planar, just counting how many cycles you might have.
Is this true whether you do this with the reds or the blues or the greens?
Well, exactly, because everything is symmetric. You can do this every which way around.
Maps, though, because planar maps have this asymmetry.
No.
The blues have to be two.
Yes, but you just generalize to planar hypermaps, and then everything is symmetrical. And the formalization actually just does its construction once, and then it just says, okay, by symmetry, you've got two other ones.
But does this operation preserve, like, if it was a planar map before?
Yeah.
Like a planar hypermap, which additionally had this constraint about the being actually related to a planar map, then would it still be a planar map?
It's still planar in the sense that it satisfies the Euler condition.
Would it still preserve this blue arrow doubling the order 2?
No. But of course, if you do it twice, then you suppress 2 points on exactly 2 points on blue arrows. Then it's going to be to work out. So. So how do you, so I said you've got three transformations, and they, what we want to do is do reductions like this that somehow preserve the shape of this bad contour. So so to do that, we're going to have to use the whole range of transformations. So the easiest thing, since the contour only talks about red and green edges, we'd like to use as much as possible the blue variant of the walk-up transform, because that's going to preserve almost all red and green connectivity. And for example, if there's a path that's completely outside of a point that's completely outside of the contour, then we can certainly apply the transform at that point, and that will preserve all the green arrows that don't come or lead from that point. So so the path will be entirely preserved. If we want to do things on the path, well, this will still work if we do something. We have some point that's somewhere in the middle here, and that has red and green on both sides, because then we can just move across. If things get more complicated, so if we have some alternation between red and greens, then we're going to have to use these variants, which are somewhat more dangerous. So for example, this variant is useful for nodes that are connected to green arrows. So if you remember, the original connections were like this. So if we had a contour that went like this or like this, through this point, then after we do the transformation, it goes this way or this way. So we're good. As long as somehow this red edge, which we just destroyed, wasn't used for something else. So it's trickier to apply the reduction in those cases, and ultimately, if you actually do the proof combinatorially, it's trickier to do the reduction in the middle of the sequence.
Are these paths injective? Are these paths injective?
Yes, yes, they're paths in the mathematical sense. So the technical definition of paths here correspond to what more modern mathematicians call trails. So the injectiveness or uniqueness condition is imposed separately. So instead, the proof just works out by trying to apply these transforms on the first few nodes in the path, and that's enough to actually do the proof by induction. So since I want to keep time for the other part, I'm going to talk about the so by the way, this is yeah, I was going to explain what the text comment has. So by the way, is this a reasonable size?
Yeah.
Okay, so this is a sort of high-level version of the proof where I've replaced all all the main subproof, which are more technical, by admit statements. And you can see that my interface doesn't like admit statements. Flags them in big ugly red. And the result is a proof that consists mostly of statements. So apart from the fact that it's all ASCII, it's it mostly reads like math. So the actual proof only starts at this line. So all the header part is setup, which is so this first line is the caucus flag jargon for saying, okay, we'll consider a minimal counterexample. So we'll do this is basically setting up a proof by induction on the size of the map.
The map is called M.
So M is the size of the map, and M gets eliminated here. So sorry, at this point. So because essentially we specialize the induction hypothesis on the three possible transforms. Because that's the only things we'll ever need. So from the get-go, we just say, okay, we'll set up. We just set up induction, and we'll use induction over these things.
Wait, so you mean to say that when you apply the E walk-up transformation, then you get something that satisfies the inductive hypothesis or something like this?
So yeah. And that means that it doesn't have a, so the typical argument is going to be, okay, we're in a situation where we know the contour will be preserved. We can show the contour will be preserved if we do this walk-up transformation. And then this contradicts the induction hypothesis for that transform.
Can you execute the first line, maybe?
Yeah.
Oh.
So here you've got like your induction hypothesis, so kind of smaller font for those, so it can sort of fit. So here, there's one factoid of the fact that the walk-up transformation gives you a smaller map. And I have no idea why my machine is atrociously slow. Oh,
I think
and
you're clicking the wrong button. Maybe you should go to font instead of processing next.
so let me move on to the start of the proof, and you can just see what I've put in the context. Doing this.
Is the double tilde just a knot?
So the double tilde is the knot. Because the double and is the Boolean knot, because the double and is the Boolean knot inside it. Okay. This is going to be a bit painful. So essentially we've got these three factoids which give us conditions on which under which contour paths can be lifted. And so for the E transform, you can lift under the minimal condition that the point which you're suppressing is not on the path. And then you need additional precautions if you're doing the other transforms. Okay, so basic facts, and this is one of the places. So even though this is mostly top-level proof, you can see that there's actually quite a fair number of imperatives in it, and that would actually be the case if you're writing up the proof. So I'm very much against the principle that proofs are only claims. My experience is that yes, they're mostly claims, and especially if you want to revise your proof so that the proof script is mostly claims. But there are places where it's really inconvenient to state things as a claim, because that ends up restating half of your context.
I have a suggestion. Could you create a translator from this into natural language, which would, because I have seen this like 5 times in your various talks, and I always stare at it, and I have no clue what's going on there.
Yes.
Could you?
It doesn't help that the blues are so washed out on the screen that you don't see where the.
But now you said that it corresponds to natural language proofs in some sense. So why don't you get it?
So here, I mean here, here's one point where at this point we're saying, okay, let's take a point y as the first point in the contour, and then this changes the whole way. Then we know that there's a contour link between x and y, so either a forward green arrow or a backward red arrow. And then there's a contour, there's the rest of the contour starts at y. And anything else that talks about the contour knows that at this point it starts with y, and we don't, and we just want to give use implicitly this information everywhere. So in a natural language proof, you would implicitly use the information everywhere, and there may or may not be mention of this in the text. It's much easier to actually tell the prover to do it everywhere and have it, because then you get more useful feedback from it. Then you can extract.
So what exactly did this case statement put in it? So what was?
So P was known to be a trail or a sequence of points, and a sequence of points is either empty or it starts with the first point. In this case, it's obvious from all the conditions that it can't possibly be empty. You don't even need to make an argument to call for it. It just figures out that some conditions, some assumptions are trivially false if your path were empty. So you thought, okay, look at the 2 cases. For one is immediately excluded, and the other one you get the first point, and then the rest of the trail. And doing this case analysis, you can just keep the name P for the rest of the trail, because it's easier than having in text proof. You might say P1, P2, P3, but this quickly gets cumbersome in working with all the other details. So let me move forward. So you extract the second point, and actually, I should probably have pointed. So the first part where you actually use the induction hypothesis is this bit, which says, okay, actually the contour has to contain the entire graph. And so that's because if it didn't, then you could do an E transform over some point that's not on the contour, and then you contradict this induction hypothesis. Here you've got, you prove that you can assume that the first arrow you're following is a green one.
The statement says face x equals y. So face is a function which does what?
So face is the function that is drawn as the green arrow. It goes across the.
Oh, so at every vertex, the
So
green
this is a
arrow
permutation, right? So you're drawing it as arrows, but it's mathematically it's a function.
So I have a much higher level question. I don't sort of care too much about the details of the actual proof, but this is about libraries, right? So if I'm staring at this, how the heck do I know which libraries are being used where? I mean, I can't see anything there that's telling me, oh, I'm now using this library or that. So where does that come in?
Well, obviously there's an import statement at the top of the file.
So what does that look like?
And it's fairly limited here because it's just imports the very basic combinatorial library, and the most important part is that it imports the library on paths and finite graphs.
So that introduces some stuff that I wouldn't have otherwise had, and I use that stuff.
Yeah, and I guess the critical part for this theory is that it imports a library that describes what a hypermap is.
I suppose what I'm asking is, if I was trying to read your proof and I wanted to know where a particular thing came from, would I be able to?
You can run it through code. That's what I did. You can write through code to create the HTML, and then you can click on every symbol.
Yeah.
And that's what I told you.
Can't I do that in Emacs buffer though?
No, because I haven't compiled tags.
Oh, I see. But if you had, you could.
Roughly, you get a quick feeling. It's helpful to actually. There aren't that many files, so it's fairly easy to know where everything should go, and then for each file, like hypermaps, for example, you have this big header that says, okay, what's defined in this? So it says, okay, for a hypermap, you have you define edge, which is the image under a first permutation node, and so on. And then
So I have a related question. In the proof itself, could you interleave comments?
yeah, you can put comments. So I tend not to do this unless it's really needed, because ultimately your biggest enemy when you are doing a large proof is to lose track of what's happening. This tends to blow up your proof size by probably an extra factor of 4, because you don't factor things that ought to be factored, or you actually redo things multiple times, or you just go about something the wrong way completely.
I could have a newbie mode for people who don't understand your commands with some.
You could have a mode where you suppress the comments.
Yeah. Oh.
So when we move to the second part,
The thing that slightly sort of makes me feel a bit queasy is that you personally are probably truly excellent at writing that comment stuff at the top, right? But you didn't have to. Somehow it would be better if the system forced you to.
Well, I'm in as much as the library is concerned, I'm pretty much forcing everyone that wants to add something to the library to do this. And there was one point where we'd fallen back in those comments, and we did a major push in documenting everything. And even you can only remember so much. So even if you've written the entire library, the only thing you actually keep in your head is the general layout. And so you want to be able to have find a quick reference point. And I find that this is sort of the right level of documentation. If you put too much stuff in the documentation, it's so long that it's too much effort to read it, and therefore you can't refer to it quickly enough. So that, and of course, if you don't have anything, or just a list of symbols, then it's simply not
Yeah, it would be nice to be able to follow the proof with the commentary, so that someone reading it can say, oh, this is the step, this is the step where you're, picking the first edge on the path and so on.
Yeah, well,
I mean,
but of course, the
also-
text, the script, if you have any familiarity with the script, either it's an imperative and the script should be is explicit about it, or it's and in a longer proof, it's going to be mostly for its statements. So let me see.
I guess that in order to read like these have statements, you have to know a lot of these definitions. And I think maybe for presentations, might be nice to have translations of like this statement is saying this in natural language, and then that'll immediately tell people, oh, that's what that bracket thing means, that's what that V space means. I don't know what any symbols mean because I can't look
This
them
could
up.
be a 1-month student job, and you will get much more propaganda out of showing this to mathematicians. Seriously.
Well, yeah, I guess.
We can
The
tell
Conc
you're
doesn't
not
have a
convinced.
LaTeX mode, and CompDoc doesn't have a LaTeX mode, and I guess my point being that ultimately this is not so nice for showing; it's very nice for working in it, because ultimately, if you work in something where the input language is the natural language LaTeX, then you're fighting the encoding every step of the way.
I get your point, but the problem, even when I look at Mizar, when I'm reviewing some Mizar article by somebody else, I first run it through something like the HTMLizer, when I can click on the symbols and I understand what he meant. So if you want to go through something which somebody else did, it's much more useful to first see it in the bloated human version, and then you gradually get into your efficient writing language. But this is really an HCI issue.
Yeah. Okay, so I have 5 minutes to show the actual algebra library. So that's the VIT proof, and so the math is more advanced here, but on the other hand, the notation is a lot more standard, because algebra is more standard than graph combinatorics. So again, I've kept it at the high level, but you get this line, for example, that says there existed two P's, so that P is a prime and P is the characteristic of R.
What is exists
This exists.
Okay.
It exists with two conditions.
Exists too.
I didn't invent this. This is a standard cock figure.
Is there an exists one and an exists?
There's an exists that's just exists.
I see.
And of course, you could have exists with an and,
Alright,
but
okay.
it's
Let's not get into
Don't you
it.
have it?
it's not so nice to use.
Don't you have an and here? It looks like you wrote exists prime P and P and.
Yeah, but it's not a separate constructor. It's part of the exists.
Oh, I see.
It's something that has two properties at once. And you typically use it to denote bounded exists. So the first step, again, the top of the proof is sort of just basic setup. And the way this proof works is by, and the reason I picked it is that it looks both at, it uses algebra and basically every linear algebra up to field extensions in order to talk about finite fields. And especially it's going to look at this finite domain as an F algebra over the integers mod p. So this is what these second and third line are setting up. They're saying, okay, well, there's a characteristic because it's finite,
Wait,
I actually have to prove it here because the generic proof only works for fields and.
so char here is a set of integers,
Yes,
and it represents all of the different characteristics
Exactly.
that it can have. Is this because of the trivial?
yes, because the this way the zero set, which is the empty set, represents the zero characteristic. And it's one of the places where you have to give a level to the constructive type theory. This way you can have the characteristic being in the characteristic be a decidable statement. So you get you get the prime characteristic. Then you've got the definitions up there to that set up any kind of ring over with a prime characteristic as an algebra over as an F algebra over the integers mod p. Then we actually define L as the full subspace of that algebra. So that's where so that's our sort of linear algebra part. And then we're going to use we're also going to use finite group theory because we're in a finite field. So we set up G as well the full group of the set of units of R. So in order to have a group, we need to exclude the well, actually here we only need to exclude the zero, but we need to exclude non-invertible elements as a rule. So there's already a setup for the properties of the groups of units. So we set up G as the group of unit, and because units and elements of the ring are different, we need to set them up as different types. And so there's an injection that goes from units into the domain. And then there's a reverse image that goes back from a subspace to a subgroup. And that typically removes the zero. And we can show that for any so we can so indeed the zero is removed because the number of elements of the projection on the group of units is exactly p to the dimension of the space minus 1. Then, of course, our goal is to show that multiplication could be used. So we're going to look at centralizers both in the field and or in the ring and in the group. And there's an obvious correspondence between the two. And so this is set up in the one line over here. So this is a centralizer of one element. This is the basically the subfield that's the center of the entire domain. And our goal is to show that the center is actually the whole domain.
What's percent AS?
So this is Cox's way of manually overloading notation. So rather than playing the game of adding little indices to notations to distinguish them, you just use the standard notation, like C of L for a centralizer, And then if it's a centralizer, here by default, the top notation is group, so by default the centralizer will be a group centralizer. So to say that it's an algebra centralizer, you say that this notation should be interpreted as algebras. And there are a number of places, tricks Coq plays so that you don't have always to put this indication here. There's no context, so I need to be specific. So the reason from the get-go, this proof is playing on two tables at once. And that's the strength of the library, of being able to take completely different parts and merging them on the spur of the moment in the middle of a proof. Somehow this is much faster than the other one. So the line I just passed is the sort of central definition. The key, the linchpin of the argument is this n here, which is the relative dimension of this of the domain over its center. So since the center is a field, we can talk about the dimension over the center. And the goal is to show that n is equal to 1. And because then if n is equal to 1, then obviously the relative dimension, it means that q is actually equal to L. It's sort of even obvious that you can just show that n is less than or equal to 1. Because it's obviously can't be 0. So you can assume that it's greater than 1 if you're going to show that it's less than 1. This is some trivial factoid. So we tend to get those even at the high level, because rather than hand-holding the prover every time it needs this factoid, you can just put them in the context from the get-go, and you generally don't have too many of them. And now this is where the proof kicks in over gear. We now bring in a third completely unrelated theory. Well, not completely unrelated, but it's a completely separate. Now we pick a complex number, or actually a complex algebraic. So we pick a primitive root of nth root of 1. So now we have, again, something that's completely different, but we can just invoke it on I haven't even put an admit here, because I can just invoke the specific theorem. And I don't, this is one case where I don't feel like I need to put any more indication that here having an imperative is just as good as being declarative. Because the name of the theorem is fairly self-explanatory. Now you have the sort of obvious properties that elevating the nth root to 1, nth power gives 1, that it has modulus 1. And next line, yet another different theory, somewhat related. You bring in the cyclotomic polynomials. So cyclotomic here is actually the factored version of the cyclotomic polynomial, using this value as the root.
What does that say? The z plus?
So that's z power n divided by d. So this is Euclidean division. So it's division in integers. So this is one case where I caved in and annotated the symbols rather than use, because Euclidean division is sort of qualitatively different from normal ring division. So I not use the slash symbol for it.
Wait, so this is producing a net or a complex number?
So this is actually producing a polynomial, though I haven't mentioned polynomials explicitly anywhere. So it's producing a polynomial whose coefficients are in complex numbers, and then it's evaluating this polynomial over Q lifted to complex numbers. So again, I've kicked. So again, I've just invoked at the on one line a completely different theory.
Sorry, what's the significance of invoking different theories like this? I mean, isn't that always possible? Like if I import a bunch of libraries, then I can use them as I wish.
No, usually not.
So
You
does it
would,
name
because
conflicts?
the typical way of setting up libraries will say, oh, you can use this theory as long as the objects are described as belonging to this theory. So you'll set up, you'll have a big set of lattice theory, but if you you see a set expression and you want to say, okay, well, now these unions and intersections behave this way because they're actually joins and meet in the Boolean lattice, well, too bad for you. You first have to explain that, yes, you need to reinterpret the expression. You can't just apply the theory directly. Or for example, another vicious thing that can happen is that you'll say, oh, well, now you have to invent, if you work with 5 different theories, you have to have 5 different symbols for the 5 different multiplications. Here there's no setup whatsoever.
So here, when you bring in this thing about cyclotomic polynomials, so your point is that you're using it with something that normally would. So it's not just the fact that you're bringing in the theories, that you're using it with things that are kind of foreign to you.
Exactly.
So what is it specifically in this case that so you're taking? Is it that you're?
I think it would probably be inside the proof, the technical limits and units, when you would relate like the AQ to these centralizers and put them all together, and it'll, in order for them to work together, you may have to have the theory, which will allow you to use it.
Yeah. So of course this is just at this point I just created the object independently. It's not so useful, but the point is I'm going to use it. So the clever bit of the proof, this is the graphical bit of the proof, which says, okay, to prove that n is less than 1, it's sufficient to prove that AQ of n is less than Q minus 1. And that's the part which is usually done by drawing a picture. Take the AQ is just a product of differences between Q and various roots of unity on the unit cycle. And now if you take the point that's Q apart here, okay, well, the difference between this, the 0th power is exactly Q minus 1. And then all the other differences are strictly greater than Q minus 1, and Q is greater than 1, so all of these are greater than 1. So the product is going to be greater than so if we have this inequality here, then the only way this can happen is if n is equal to 1. So that's the So this is a completely so this is an argument in a sort of really completely different theory, because this is talking about inequalities of real numbers, or in this case, the theory is set up so that we can actually state it as an inequality of complex numbers using line-by-line ordering of complex numbers.
An ordering of complex numbers?
You can have a partial ordering of complex numbers horizontally, and that contains the real the real line. And surprisingly, most of the lemmas that you'd expect to have for the real numbers generalize to complex numbers under that order. You can almost there are very few lemmas where you need to say something is actually real. Because anytime you need to you depend on something being non-horizontal, so when you're multiplying, actually you need that thing to be positive. Right? If you're multiplying a real inequality, you need to know whether it's positive, or you're multiplying by something positive or negative. And of course that immediately tells you that's also real. So ultimately all of the theory looks like the normal, almost all the theory looks like a normal theory. It's only in the case where you say, okay, it's a square, it has to be positive, then you need the thing inside the square to be real. Well, that's very occasional. So that bit here is a part where there's, underneath this proof, there's a completely different theory used again. Because this is showing that this polynomial is valued in integers. And the reason is, it's because it's a cyclotomic polynomial, so it's actually a polynomial with integer coefficients. So it's the image of a, so it's really talking about a polynomial inside the integers. And the proof uses the four-line proof, which I've compressed here, uses that. And uses this, and here you see the sort of first example of these closed algebraic predicates. So we have a predicate defining the integers among all the complex numbers. And anything that, all the character theory development relies heavily on this. See, I'm almost done through the proof. Well, I'll talk my head off. So then we just prove a the expansion formula, which exists in a slightly different form in the cyclotomic library. So in this case, there's a bit of proof, really technical proof going on that probably would be skipped over a math proof saying, okay, it's the same thing. You can work out the details, but Coq is not smart enough to work out the details here. So it needs a little hand-holding to say that, okay, we need to go through so we need to change the q to the m-1 to this polynomial applied to this, and then we can use the expansion of x to the m-1 as a product of cyclotomics. And then there's a bit technical bit to complete the proof.
We can cut to the chase.
Yeah. So then the part where you invoke the group theory is when you realize that AQ of n will always divide, because of this formula, will always divide the order of the group itself. Because then it's the product over all the divisors. And so it contains AQ of n divides the order of the groups it divides. AQ of n divides is one of those factors. So we can add the order of the group in front, and then it's going to be enough to show that a Q of n divides the order of every class. So a class is this object defined in the very first finite group file, which is just all of the, you take the orbit of a given element under the conjugation action of G. So you take all the conjugates, y minus 1, x, uy for y ranging over all the G's. And there is this general orbit formula which which is specialized to those orbits, which gives you expands the number of elements in G into the sum. And so, well, now you see that this top bit here, the number of elements in the center, that's exactly Q minus 1, so those are going to cancel. And then the assumption I've got here means that every single one of those factors is going to be divisible. So, so at this point the proof is trivial. And then we have a bit of another bit of group theory to show that the order of this is actually given by another product of AQs when you take all the divisors of n but remove the divisors of m, where m is the relative dimension of the centralizer here, which means and because we've got the assumption that u is not in the center, then n is not going to be a divisor of m. So we're going to get, we're again going to get this AQ of n factor in there. And that basically finishes the proof. And that's the last thing. So this is the proof with all the details filled in. And obviously I don't expect you to read any of it, just to see that the size of the things that have been omitted, it's never more than 4 or 5 lines. So in an ideal system where we could have write a top level proof that is probably some, we wouldn't expect an automated system to find the top level proof on its own. The part we're missing, and if we had ideal automation, it would just need to handle those 5-line proofs. Or on the other hand, the automation we get from the higher order logic and having all the concepts in the library is such that we're just 4 lines above the sort of graduate course level of detail. Probably a factor of 10 behind the highbrow research fields medalist level of write-up. Okay, well, thank you for your patience.
In Brian's writing, he has more or less the same kind of conception of the use of libraries that you have, except there's this notion I think he has called a telescope. Is that right term? So your use of library seems to kind of have this you're telescoping into the.
So what's important is that the libraries can cooperate on the same objects, so that you can get you're not forced to work entirely in one world or entirely in a different world. And in proofs like this, you need to work in I'd say at least 3 different worlds here. 4 if you count the basic arithmetic and prime numbers. And these all have to, and you have to, and you're doing things in the same line. You might be doing things in all 4 different worlds at once. So having you, forcing you to switch modes or switch completely from frames, proof search frames, from one part of the line to another one is kind of a non-starter.
I think that's what this telescope mechanism was like. I only have a vague recollection of it.
It relies on being on the use of type classes to be able to align concepts across.
It allows you
across
to kind of
libraries.
reach into a context you created and pull it out into your current context.
It's being able to tell a different library that it can work on the objects you're interested in, because they have the properties and operations that the library expects. That's sort of what type classes do, but you need a little more than type classes because you need to be able to do it at the object level, not just at the type level. So the type, you have to sort of remove the type from type classes. So in some cases, it's enough to know that you've got a group structure over this type, or that this type is finite. But in other cases, you need actual properties of the objects. You need to know that the operation that's being iterated in this sum is commutative and associative. You need to know that this predicate of integers is closed under sums. And that's and if you have to supply that information at the point where you want to use the library, then that becomes an obstacle to using the library, and one that can be make it not worthwhile. In some sense, I think that's why proofs tend to bloat so much, is because there's sort of incidental costs that add up and make it not worthwhile to develop libraries.
Right.
And then if you don't have the libraries, then you'll eventually get stuck up at points where, yeah, even with the overhead, the library would have been useful, but you're set up your way of doing things. And
so another thing I noticed is that the labeling plays a kind of important role. Is that SS reflect or?
So SS reflect doesn't. What SS reflect gives you is an easy way of getting rid of things when you don't need them anymore.
Like the admit, no, that's something you're suppressing. But,
Yeah, also it happens here, for example. So here I'm showing this property, and here I'm removing it from the context. So that's essentially what it gives you pruning, but it's encouraging you to name things, and then the author of the proof in this case has his particular way of choosing names, so that they actually help reading the proof. So the first line of defense in trying to understand what the statement means, apart one that that's not straight math, but one of the more imperatives, is to understand what the various facts that are invoked mean, and having the name being so obviously, if you set things up nicely, you can just click on the symbol or over the symbol and see the definition. But it's even better if the name itself tells you what's going on at a first glance, because you don't need to hover over each one of them to figure out what's going on. I've definitely moved away from the style of naming that sort of derived from math, of calling all your facts H1, H2, H3, H4, H5. Really not helpful on a computer system.
But the thing is that your idea of what's a helpful name won't be the same as mine. So I will have to hover over it and see the definition.
At first, yes. Hopeful. If you see a proof out of the blue, it's that's sort of likely. I'm gather you'll get more information from that name than H33. I can tell you that much.
Yeah, I think we could agree on that.
But I think the usefulness of H33 or saying fact 3.57 is if you're on a physical page, it helps you find it by bisecting.
Sure.
This isn't a problem in a computer system. So you might as well have names that are somewhat useful. Of course, there will compromise between being very descriptive and being reasonably short. I probably err on the short side. But then that's because if things become very long, then you lose track of what's going on, and it becomes harder to keep your proof under control because at some point the system gets the better of you.
Chet Brown just writes the formula, and then it does its MD5 hash, and if the formula is already an accepted theorem, then it looks up in the database of MD5 hashes. But he doesn't have any need for labels. He always writes the full formulas.
It would be nice if there was some semantics in the hashing as well.
Yeah, Lean has something like that, where you say, okay, the proof of this thing, but generally the name is quite a bit shorter than the statement. So it's
also than the MD5.
Yes.
And the MD5 would be subject to trivial variations in syntax.
You said something about clearing hypotheses after you're done using them.
Yes.
Where is that indicated?
So that's anytime you have something in curly braces.
Oh, that's right.
It's actually one of my refactoring passes to add as many of those as I can, because then it actually states, you can read those as this statement is using this, the M is an equation for M. And so this statement uses the equation for M, and this is where we use the assumption. And I've often found improved proofs significantly just by tracking that information, because then you realize that oh well, then there's this fact I don't need to carry this long. I should regroup these two subproofs, or in some cases actually this fact isn't used at all. Let me remove half a page of the proof, which the author of the textbook wrote down only to impress the reader, but not to actually prove his theorem.
Okay, so let's thank John.